Let's look at an example where we suddenly apply a DC source to a circuit. We'll look specifically at an RL circuit. So we could show that we have a DC source and we use at our time, we'll call t is equal to 0, we switch that source into the circuit. And that maybe is physically what happens, but we could model our V0 voltage source and our switch with a voltage source with the function V0 u of t, applying our unit step function mathematically to our ideal voltage model. So what we know is before t is equal to 0, our current is equal to 0 in this circuit. There can't be any current flowing because it's open. And for u of t, before t is equal to 0, u of t is equal to 0. So this is the perfect model for this situation. So if we write our KVL equation, then we have the voltage across the resistor, Ri, plus voltage across the inductor, L di dt in this direction, is equal to our V0 u of t in this direction. So that's our KVL equation. When we looked before at a source-free circuit, it was equal to 0. Now it's equal to our V0 u of t. Well, remember that u of t, that's a piecewise function. So when t is less than 0, our Ri L di dt plus L di dt is equal to 0. But when t is greater than 0, it's equal to V0. So we basically have two functions here to evaluate. But what we do, if we consider this circuit has been this way since negative infinity, then the current in the inductor will be equal to 0 for t less than 0, and we're all set there. So we met our initial conditions, we wrote our KVL equation. Now we have to evaluate. We've already evaluated at t less than 0, our source-free RL. Let's evaluate this differential equation here for t greater than 0. So our t greater than 0 KVL equation, V0 is equal to Ri plus L di dt, where we have our initial condition, I of 0 minus is equal to 0. So we can separate the variables and integrate. When we separate the variables, we bring our I to the other side of the equation. So basically we end up with V0 minus Ri is equal to L di dt, and then we can bring our dt over to this side of the equation, dt, and then bring our V0 over Ri to this side of the equation. And then we integrate. So our integral, we're integrating dt. That's the integral of dt is equal to the integral of L times our di divided by V0 minus Ri. Well, that integral will still give us a natural log function, but we also have to pull out 1 over negative r. So we're both sides, we're doing our indefinite integral, so we'll have a constant of integration. We'll just combine those two constants of integration and evaluate the constant of integration on the left-hand side of the equation. Since it is an indefinite integral, then what we want to do is use that constant of integration to determine what the initial conditions are, solving for the constant of integration, with the initial conditions. So again, we've evaluated the integral. We'll now apply our initial conditions. Our I, when t is equal to 0, then our I is equal to 0. So we can plug t is equal to 0 here and plug I is equal to 0 here, and we find that our constant of integration k is negative L over R natural log of that V0, the amplitude of our voltage source. So now that we have our constant of integration, we can plug that back into this equation up here, and we get t minus L over R natural log of V0 is equal to negative L over R natural log of V0 minus Ri. So we still want to isolate t, and we want to get rid of this natural log function. So if we multiply through by negative r over L, then we end up with a negative r over L in front of the t, and this will just become positive 1, and this become a positive 1, and then we can subtract natural log of V0 and pull it to this side of the equation, and then we can use the property of the natural logs, where the difference of two natural logs is equal to the ratio of the natural log of the two arguments. So we end up with our natural log of our voltage V0 minus Ri divided by V0 is equal to that negative R over LT. So now we can take the exponential of both sides of the equation, and we get this, what we now are familiar with, e to the negative r over lt. And that should be a negative sign there. It looks like just an extended fraction sign. But so now we see this e to the negative r over lt, which we have found out that's the natural response of this inductor in an RL circuit. So that makes sense. We do have our voltage source here, V naught, but we might want to separate that out. You know, we want to solve that now for I. Our current then is equal to V naught over R minus V naught over R e to the negative R over LT. And that's, we were solving for it at t greater than 0, so that's what's true at t greater than 0. We could write that also, you know, as instead of as at t greater than 0, since it's also equal to 0 at t less than 0, we can write it for all time by multiplying the sum of these two terms by u of t, and we solved that for all time. So interpreting this solution, let's take a look here. If we see that we do have this source-free response here, at least has the form of the source-free response, this exponential function. And then we have this other term that is being added to it. But our source-free response at a e to the negative t over tau, where our time constant for this circuit is 1 over R over L, or it's equal to our L over R. That's so we know our time constant, same time constant of a source-free circuit. Our amplitude, that's V naught over R. That amplitude is going to depend on the forcing function. This is going to depend on the nature of the circuit. It's basically our LEQ over REQ. Right now we just have one L and one R. But that's always going to be that form of our source-free response. The transient response, again, that's source-free or transient or natural response. It's subtracted from this V naught over R, which has the form of the forcing function. So our transient is resisting the change in current that's being forced upon it when we switch this forcing function into the circuit. So our force response V naught over R, that's what remains after the transient dies out. So once the transient dies out, we're back in DC conditions. Then remember, our inductor just looks like a short circuit, so the current's just going to be V naught over R. And that's what we would expect from this circuit, and that's what we get when we interpret this solution. So a general solution, a current is going to be equal to, in our RL circuit, it's going to be the current at time is equal to infinity. That's our forced function, our forcing function. So that's essentially equal to our IF. And then the current at 0 plus minus the current at infinity times the form of our natural response. So this whole other thing over here, that's our IN, that's our natural response. The amplitude, or that arbitrary constant A of our natural response, that is a function of both the initial conditions and the final conditions. So for our RL circuit, that's V naught over R minus V naught over R e to the negative R over LT for just this simple RL circuit here. The voltage, however, across the inductor, we can also find that's L di dt. So when we take the derivative of this with respect to time, the derivative of the forced response, V naught over R, that's just equal to 0. So we just have to consider the derivative of this portion. Our U of t, that's just 1. So by chain rule, we don't need to consider that. So that's going to be our L, due to this L, right, times our R over L, then our V naught over R e to the negative R over L, where the R's are going to cancel, right? So we just end up with, and the L's are going to cancel, we just end up with our V naught e to the negative R over LT. And what we'll find is that V naught, that should really be a capital V because it's a capital over here. But that's our voltage source, right? So initially, all this voltage drops across our inductor here, and then it dies out over time. Whereas what's happening with the current is increasing over time. So we have our current function, is here. We could write it as V naught over R 1 minus e to the negative R over LT. So that function is going to increase with this form when t is equal to tau, or after one time constant, where 1 minus 0.368 or is 0.632 of our final response. Within 3 time constants, we're within 5% of that final value. What was happening with the voltage, however, our VL was 0, and then it spiked, right? It spiked up to V naught, and then it died out. So within one time constant, if we let that have the same height, within one time constant, it was going to be down here at 0.368, and that of V naught. So this is our VL, and this is our IL, current through the inductor. All right, that's it for this video.